Hello again. Now we're going to have a quick talk about electronics for the Internet of Things. This is a very basic introduction to electronics for anyone who hasn't had a great deal to do with them before. We won't be going into much of the theory, just a practical application of things we need to know to build our lab experiments for this weekend. So what we'll be looking at is some signals, very basic Ohms Law, how we work with the GPIO or general purpose input-output, pulse width modulation on the microcontrollers, how we get our analog signals into a digital format, and just a little bit more on the microcontrollers and computers. So generally, here we have some signals, electronic signals, analog versus digital. I'm pretty sure everyone knows about this, but we'll just run over it very quickly again anyway. Digital signals are simply on-off. That's all they have. Two states, binary, why they're called digital. Analog signals are completely different in that they are continuous time and their meaning is held in the value and the frequency, not just the level. We have a simple digital signal on the left, which is just an on-off signal. Underneath that is a sine wave, nice periodic signal. Generally our analog signals don't look like that, but it's a good way of showing the altering amplitude and frequency. On the right we have a slightly different digital signal, in which case a period of each of the high levels, the ones, are of different periods, and a very random scrawl of an analog signal underneath. In microprocessors we can only store digital signals. It's not possible to store analog, so we have one or several bits per sample. We store an array of numbers, and the parameters for these samples is the bits per sample, that is the accuracy of each sample, and the sampling rate, how fast we sample. Audio recordings generally come in two basic types. We've got analog and digital. Analog refers to audio recording using methods that basically replicate the original sound waves. Vinyl records, cassette tapes are examples of analog mediums. Digital audio is recorded by taking samples of the original signal level. As we can see from the graph here, we take samples of individual levels. We then reconstruct the original signal from those samples, and we'll have a closer look at that in a sec. CDs, MP3s are examples of digital medium. Pretty sure we all know that. Now, when we're talking about bits per sample, this is how accurate we can make the reconstruction of the signal. If we only have one bit per sample, it only gives us a low for a 0, for example, or a high as a 1, purely digital. Or we can have n bits per signal sample, and that gives us 0 to 2 to the n minus 1 possible values for each sample, meaning we can get a finer granulation of the input signal and the input signal level the more bits we use per sample. We can see in this diagram we've got a continuous signal and we're taking samples from those red lines. Each sample is stored as a binary number representing that particular voltage level, and when we recreate the discrete digital signal back to its values, we only have those samples to go by. This means we end up with a somewhat step-like reconstruction of the original signal. This is termed quantization noise. Sampling rate is a little bit different, and this relates to Nyquist theorems. The faster we sample, the higher the accuracy of our reconstruction. Our sampling frequency must be at least 2 times greater than the maximum frequency component in a signal. If we take the example of voice, that is generally 300 Hz to 3.4 kHz or 3.6 kHz, around about there, we need to sample that at least twice the highest frequency component of that voice signal. Highest frequency component of voice in our example is 3.4 kHz, so we would normally sample that at around 8 kHz. And we can see in the diagram here, as we increase the sampling rate, we get a closer representation or reconstruction of the signal was input. When we're sampling very low rates, the signal doesn't really look much like the original, but as we increase the sampling rate, the reconstructed signal becomes a little bit more accurate compared to the input. Now we need to look at some electronic components. We're only going to be looking at a few in our laboratory sessions this weekend, but the ones we need to know about are both passive and active. Active circuits contain active components, that is, components that rely on some external power source to control the flow. Passive circuits contain passive components, components that are incapable of controlling current flow. Active components contain active components, components that rely on external power source to control the current flow. An example of this would be a transistor. A transistor requires an input current into the base, one of the connectors, to affect the current flow through that transistor, so you actively control the current. Passive circuits contain passive components, and these are the components that we don't control the current for. It's set. So for example, a resistor is used to act as a voltage divider, or basically to limit the current flowing in a circuit. It limits that current irrespective of any effect we try to have on that component. So we can't control it in any way. It's fixed. It doesn't change. It acts passively within the circuit. Analog circuits are circuits where all the signals are contiguous. In other words, they just continue over time. And these are the sort of circuits we need to convert into a digital or a discrete time signal for our processing. Direct current versus alternating current, fairly straightforward. In DC, direct current, electron flow is in one direction only, and you get this from a battery, for example. Power supplies, solar cells, they all generate DC. In AC current, electron flow periodically reverses, generally at either 50 or 60 Hertz or 50 or 60 times per second. Okay, let's have a look at the layout of circuits. Here we have series and parallel circuits. A series circuit is where the components are interconnected one after another in a single path between the positive and negative terminals of the power source. This means that current through both components is the same. In a parallel circuit, we have components connected in parallel, and the current branches, one path through one component, the other path through another component, for as many parallel components as we have, and the sum of these branch currents equals the total current of the circuit. The main one we'll be looking at is only for the series circuits though. And for series circuits, we only have to look at Ohm's law in a very simple matter. The current through a circuit is equal to the voltage divided by the resistance. This is Ohm's law, we've probably seen it before. Here the current in amps equals the voltage in volts divided by the resistance in ohms. So our simple circuit in this diagram here, we have a 10 ohm, a 50 ohm and a 60 ohm resistor, giving us a total of 120 ohms because we add up the resistances in a series circuit, and a 3 volt supply, the battery down the bottom here, supplying 3 volts. So if we add up the resistance, 120 ohms, we have 3 volts, that will give us 25 milliamps or 0.025 amps flowing through this circuit. Because it's a series circuit, there is only one current path, therefore the current is the same through each of these components. Now, importantly, and this is where we use it, once we know what the overall current is, or the current through the circuit is, we can work out what the voltage drop across each resistor is. In this case, we have 25 milliamps going through a 10 ohm resistor, which gives us 0.25 volts from simply applying Ohm's law. Importantly, if we look at this circuit and we add up each of the voltage drops across each of the resistors, remember we have this constant current through the circuit, only the resistance is changing, and if we add up these voltages, they will add up to the supply voltage. Important point. Okay, so how are we going to use this very simple Ohm's law? Well, basically we use it in a voltage divider type network. Here we have a voltage applied to R1 and R2, and we tap off the middle between R1 and R2, and we get a voltage which is related to the ratio of resistors R1 and R2. So we add up the resistance of our series circuit, R1 plus R2. We calculate the current through that circuit, V in divided by R1 plus R2. We then need to know what the voltage drop is across R2. That will give us V out with respect to ground, the voltage across R2. So we have our current through the circuit, we multiply that by R2, and that gives us V out. So that's where our voltage will be read from. If the resistors are equal, we will get half of V in as V out, because there is an equal voltage drop across both resistors. Otherwise, it's a ratio of the two resistors. So if R1 approaches 0 volts, what's V out? Well, basically, it's the same as V in, because we're connecting directly to V in. If R1 goes to infinity, V out is basically connected to ground, so therefore it would be 0 volts. In the labs, we're going to be using a transistor as a switch. It's very similar to a voltage divider, except we're using an active component. Transistors can be used as a switch by turning them on and off, and to do this we apply a voltage to the base, or the control, of a transistor, as we can see here with the control lead going into the base of Q2. If we apply a voltage to the base of Q2, the transistor conducts. Once it starts to conduct, we get current flow through the motor to ground, and the motor will turn on. And that equates to the simple circuit on the far right there that shows the transistor just acting as a switch. So basically, we apply a voltage to the base of a transistor, the transistor starts to conduct, and we get current flow through M1, the motor. Don't worry too much about the diode. It is there for back EMF protection, and it's only there to protect the transistor and the motor. So, why do we want to know this? Well, we use it on our output and input on GPIO digital pins. Digital pins have only two values. They are either low, which is normally 0, or high, which is normally a 1. Each pin acts like a battery if we set it to an output, or a voltage meter if we set it as an input. Low is 0 volts, so never connect it to the supply voltage or you'll short things out and something will cease to function. Also bear in mind that high is either 5 volts, 3.3 or 1.8 volts depending on the type of board that you're using. They all have different supply voltages. So when we want to read a pin, we go back to our voltage divider. We remember that it was the R1 plus R2 and the ratio set to our voltage at V out. Well, we can use this is an input. In the circuit we have here a switch connected to VDD, which is our supply voltage, and a resistor to ground. When the circuit is open, the switch is off. The only connection that we have is to ground through that resistor, the pull-down resistor. Right, so that means that pin 1 would be at 0 volts. If we can close the switch, we connect pin 1 to the supply voltage, which means it would be a high, and we would read pin 1 as high. This we could then use to output on pin 0. If we set it low, it's 0 volts on both sides of the LED that's in the diagram there. If we set it high, we have 5 volts on the anode of the LED, which means it will conduct and glow. And that means as we turn the switch on, we can then turn the LED on. You'll see how to do this in software when we get to that particular section. Another very important aspect we have is pulse width modulation. Pulse width modulation is a way of controlling the power output to a device. We use this in LEDs. The greater the pulse width, the more power outputting to the LED, therefore the brighter it is. We also use it in positioning of servo motors, and we can use it for motor speed as well. We set the percentage of the high duty cycle to create this power level. 0 is 0%, and we're using an 8-bit pulse width modulator on the Arduino boards, so that gives us a value of 255, which would be 100%. But this very much depends on the library you're using and how it's implemented. So if we wanted a 50% duty cycle, we would set it to either 127 or 128, depending on where you started your counting from, and we would have the signal turned on for 50% of available time. So if we look at the graphic, we can see when we have a 0% duty cycle, 0% of the time is set high, or at 5 volts in this case. We set it to 50% duty cycle, and it is 5 volts or high for 50% of the time and 0 volts for 50% of the time. If we set it to 100%, then it's at the high level 100% of the time, and that would equate to the 255. We also need to just quickly go over the microcontrollers again and computers and the difference here. Microcontrollers are simple systems. We use them to control hardware. They are generally low speed and have small memory. Quite often they will have a reasonable amount of general purpose I/O, that's lots of pins so that we can have things controlled directly by the microcontroller. They will generally have a built-in pulse width modulator and analog to digital converter so we can read analog signals in. And they run a single application program. They run one program and one program only. Generally they don't have an operating system and the software resides in firmware, which I'll explain in one sec. Microcomputers have a full CPU. They generally run at much higher speeds, have a larger memory, limited GPIO, but they generally still have some GPIO, and they generally run an operating system. In our case, we're running Linux. The software itself, a couple of bits of terminology. In a normal computer, we have software, all really familiar with that. It's a program that's written, it's stored on a hard disk, you load it into memory, and it executes. That's just normal software. On a microcontroller, it's normally not that way because we don't have storage devices. We don't have SD cards, we don't have hard drives, or anything else attached to them. So this program resides in hardware. It's still a program, so it's still software, but it's sitting in hardware, so therefore it's called firmware. And this is what we run on the Arduino Uno. It's there even when the power is turned off. As soon as you power it up, it starts executing that program again. Right, well in this case, since it's a recording, we can't have any questions, but hopefully we will be live and we will have a question session.